Have you ever wondered why you feel alive? Why there's a vivid inner world behind your eyes, while the brain is just cells and signals? This is the ultimate mystery. The origin of consciousness. The mystery of consciousness is perhaps the deepest and most unsettling question science has ever faced. At its core lies a simple yet profound observation. No matter how deeply we study the brain, no matter how many neurons and synapses we map, the vivid first-person experience of being alive remains unexplained. This enigma is famously known as the hard problem of consciousness, a term coined by philosopher David Chalmers. It separates the mechanical workings of the brain, the way neurons fire, the way information is processed, from the subjective inner world we inhabit. Why should electrical signals in gray matter produce a sense of I? Why does seeing the color red feel like something, rather than just triggering a mechanical reaction? This is not merely an academic puzzle. It strikes at the heart of existence itself. For centuries, thinkers and scientists have tried to understand how consciousness emerges. Ancient philosophers like Plato and Descartes speculated about the soul, believing that the mind was something immaterial, distinct from the body. Descartes famously declared, "I think, therefore I am," anchoring existence in thought. But modern neuroscience takes a very different approach. It sees the brain as a biological machine, made of neurons, chemicals, and electrical signals. And yet, even with this powerful framework, there's a glaring gap. We can scan brains and see activity patterns correlated with pain, love, and fear. But we don't know why those patterns should lead to actual feelings, why there's something it is, like to be you, instead of nothing at all. This gap between brain activity and subjective experience is what makes the hard problem so terrifying to science. Most scientific questions deal with objective facts: how gravity works, how cells divide, how stars are born. These are all third-person phenomena. But consciousness is first-person. You can't directly measure someone else's experience. You can only infer it from their words or actions. This fundamental difference challenges the very method science relies on. How do you study something that cannot be observed or quantified from the outside? It's as if we are trying to shine a flashlight on the beam of light itself. The tools we use to analyze the world seem incapable of grasping the essence of mind. One idea is that consciousness might emerge from complexity. According to this view, when a system becomes complex enough, like a brain with billions of interconnected neurons, consciousness arises as an emergent property. It's like how wetness emerges from individual water molecules, even though no single molecule is wet. But critics argue this analogy is misleading. Wetness is a property we can explain in physical terms. Consciousness, on the other hand, involves subjective experience. There's nothing in physics or chemistry that predicts why a brain should feel anything at all. Complexity may explain intelligence and behavior, but it doesn't explain why there's an inner movie playing inside your head. Another theory suggests that consciousness might be fundamental, like space and time. In this panpsychist view, even elementary particles could possess tiny flickers of experience. The universe, then, would be suffused with proto-consciousness, and the brain acts as a kind of amplifier. This sounds mystical, but it's gaining traction among serious scientists who are frustrated by traditional approaches. If consciousness can't be reduced to physical processes, perhaps it must be taken as a basic feature of reality. However, this raises further questions. If everything has consciousness, why does your experience feel unified and distinct? And how do tiny conscious particles combine into the rich, seamless awareness you feel right now? The inability to solve this mystery has led some to speculate that consciousness might forever lie beyond science. Perhaps our brains are simply not equipped to understand themselves fully. In the same way, a dog cannot grasp quantum mechanics. This idea that the human mind might have built-in limits can be deeply unsettling. It suggests there are aspects of reality that we can never access, no matter how advanced our science becomes. Some even fear that consciousness could be an illusion, a clever trick played by the brain to convince us that we are more than biological machines. But if consciousness is an illusion, who or what is being fooled? Philosophers like Thomas Nagel have also pointed out the strangeness of trying to explain consciousness from an objective perspective. In his famous essay, "What is it like to be a bat?" he argued that even if we knew everything about a bat's brain and behavior, we would still not know what it feels like to be a bat. This what it is like quality is the heart of the mystery. It suggests that consciousness is inherently subjective and cannot be fully captured by objective science. This does not mean science should stop trying, but it highlights the unique challenge posed by the hard problem. The implications of this mystery stretch far beyond philosophy and science. Consciousness is the foundation of everything we value. Without it, there's no joy, no suffering, no meaning. Understanding consciousness could transform medicine, allowing us to better treat mental illness, brain injuries, and perhaps even extend consciousness beyond biological death. But until we solve the hard problem, we don't even know how to define consciousness precisely, let alone manipulate it. This ignorance has practical consequences. For example, if we create artificial intelligence, how will we know if it is truly conscious or just simulating consciousness? Could we unknowingly create machines that suffer? Some scientists argue that progress is being made. New tools like brain imaging, neural networks, and computational models offer glimpses into the workings of the mind. Theories like integrated information theory attempt to quantify consciousness, proposing that it corresponds to the amount of integrated information in a system. Others look to quantum physics for answers, suggesting that consciousness might arise from quantum processes in the brain. Yet these ideas remain controversial and unproven. Each breakthrough seems to raise as many questions as it answers. As we probe deeper into the brain, we may also be forced to confront uncomfortable possibilities about free will, personal identity, and the nature of reality itself. If consciousness is just a product of physical processes, are we nothing more than biological robots? Do we truly have agency, or is the sense of self an elaborate hallucination? Or, conversely, if consciousness is fundamental, does it suggest a universe more alive and mysterious than we ever imagined? These questions are not just intellectual curiosities. They cut to the core of how we see ourselves and our place in the cosmos. Ultimately, the origin of consciousness remains an unsolved mystery that terrifies science because it challenges the very framework of scientific understanding. It exposes the limits of reductionism and forces us to grapple with the most intimate aspect of existence. Every moment you spend thinking about this mystery is itself a demonstration of consciousness, a strange loop where the thing we are trying to explain is also the thing doing the explaining. Perhaps the answer lies not in dissecting the brain, but in radically rethinking what reality is. Or perhaps, as some suggest, consciousness is the one thing science can never fully grasp, because it is the lens through which we see everything else. And so, the question lingers. Why does anything feel like anything? Why is there a world lit by awareness, rather than a cold, unconscious universe? Until we find an answer, consciousness will remain the ultimate enigma, a mystery that not only terrifies science, but also reminds us of the profound strangeness of simply being alive. The nature of dark matter. The universe is vast and full of secrets, but perhaps none are as haunting as the unseen mass that silently shapes the cosmos. Astronomers call it dark matter, an invisible substance that does not emit, absorb, or reflect light. We cannot see it, touch it, or directly detect it with even our most sensitive instruments. Yet its gravitational pull is undeniable. It bends the paths of stars and galaxies, sculpts the large-scale structure of the universe, and holds galaxies together like an invisible glue. Without it, the cosmos as we know it could not exist. And yet, despite decades of searching, we still don't know what dark matter is made of, or if our understanding of gravity itself is fatally flawed. The story of dark matter begins in the 1930s, when astronomer Fritz Zwicky studied a distant cluster of galaxies called the Coma Cluster. He noticed something strange. The galaxies were moving so fast that, by all rights, they should have flown apart. The visible matter, the stars, gas, and dust, simply didn't have enough gravitational pull to hold the cluster together. To explain this discrepancy, Zwicky proposed the existence of dunkle materie, or dark matter, some invisible mass that supplied the missing gravity. At the time, his idea was largely ignored, dismissed as an oddity of measurement. But the evidence has only grown stronger in the decades since. Later, in the 1970s, astronomer Vera Rubin provided some of the most compelling observations supporting dark matter. She measured how stars rotate around the centers of galaxies. According to Newtonian physics, stars farther from the center should move more slowly, much like planets farther from the sun orbit at slower speeds. But Rubin found something astonishing. The stars on the outer edges of galaxies were orbiting just as fast as those near the center. This implied there was far more mass present than we could see, an enormous invisible halo enveloping each galaxy, providing the extra gravity needed to keep the stars from flying off into space. Since then, the evidence for dark matter has only multiplied. We see its fingerprints in gravitational lensing, where light from distant galaxies is bent by the gravity of unseen mass along its path. We see it in the cosmic microwave background, the faint afterglow of the Big Bang, which reveals subtle ripples shaped by the gravitational influence of dark matter. Computer simulations of the universe's evolution also require dark matter to reproduce the structures we observe today. Without it, galaxies would never have formed as they have. But what exactly is dark matter? This is where the mystery deepens. It does not emit light, so it cannot be made of ordinary matter, atoms, protons, electrons, the stuff that makes up stars, planets, and people. Instead, scientists believe it must be something entirely different, perhaps a new type of particle that does not interact with light or electromagnetic forces. One leading candidate is the WIMP, or weakly interacting massive particle. WIMPs are hypothetical particles that would interact with ordinary matter only via the weak nuclear force and gravity, making them almost impossible to detect. Enormous underground detectors have been built to catch even a single interaction between a WIMP and an atom, but so far, they have found nothing. Another possibility is axions, ultralight particles that could fill the universe like an invisible field. Unlike WIMPs, axions would be so light and so weakly interacting that they could pass through planets and stars without leaving a trace. Physicists have designed clever experiments using powerful magnets and resonant cavities to detect axions. But again, no definitive evidence has emerged. There are even stranger ideas. Perhaps dark matter consists of primordial black holes, tiny remnants from the earliest moments after the Big Bang. Or maybe it is made of an entire hidden sector of particles, an unseen mirror universe with its own forces and interactions. The inability to detect dark matter directly has led some scientists to question whether it exists at all. Could the laws of gravity themselves be incomplete? Modified Newtonian dynamics proposes that at extremely low accelerations, like those experienced on galactic scales, gravity behaves differently than Newton predicted. This could, in theory, explain the strange motions of stars without invoking invisible mass. However, Mont struggles to explain other observations, like the cosmic microwave background and large-scale structure formation, where dark matter provides a more natural fit. What makes dark matter so unsettling is not just that we don't know what it is, it's that it dominates the universe. Ordinary matter, the kind we're made of, accounts for only about 5% of the universe's total mass and energy. Dark matter accounts for roughly 27%, with the remaining 68% made up of an even more mysterious entity called dark energy, which drives the accelerated expansion of the universe. In other words, everything we see, stars, galaxies, nebulae, all of it, is just a thin layer of froth floating atop a vast, unseen ocean. We are living in a universe where most of the matter is invisible, untouchable, and almost unknowable. The search for dark matter continues with ever more sensitive experiments. Underground detectors are shielded from cosmic rays by miles of rock, hoping to catch rare interactions. Particle accelerators like the Large Hadron Collider smash protons together at near-light speeds, hoping to create dark matter particles. Astronomers scan the sky for faint gamma rays that might result from dark matter annihilations. Each experiment brings us closer to an answer, or to the realization that we may be looking in the wrong place entirely. If we do discover what dark matter is, the implications will be profound. It could reveal entirely new realms of physics beyond the standard model, perhaps opening the door to hidden dimensions or new forces of nature. It could help us understand how galaxies formed and why the universe looks the way it does. But if we fail to solve this mystery, it would force us to confront the possibility that the universe is stranger and more alien than we can imagine. Dark matter is terrifying to science because it reminds us how much we don't know. For all our telescopes and theories, we are still largely in the dark, literally. The universe appears to be built on foundations we cannot see, understand, or directly measure. It is an invisible architect, shaping the cosmos while remaining forever out of reach. As we peer deeper into space and probe further into the quantum world, we may find answers, or we may find an even deeper mystery waiting beneath the surface. Perhaps the most humbling thought is this: you, right now, are floating in a sea of dark matter. It flows through you and the earth, unseen and unfelt, as it has for billions of years. The stars themselves owe their existence to its gravity, and yet we do not know its face. We only know its shadow. The Fermi paradox. The night sky is filled with stars, and around those stars are countless planets. Many of those planets may be like Earth, rocky, temperate, and possibly home to liquid water. With so many worlds scattered across a universe billions of years old, it seems almost inevitable that intelligent life has arisen elsewhere. And yet, as we listen to the cosmic silence, we are confronted by an unsettling question. If the universe is so vast and so ancient, where is everybody? This is the essence of the Fermi paradox, a mystery that haunts astronomy, philosophy, and even our sense of cosmic belonging. The paradox is named after physicist Enrico Fermi, who in 1950 posed a deceptively simple question during a casual lunchtime conversation. Where is everybody? Fermi realized that even if intelligent life is rare, the sheer size and age of the galaxy should make encounters with alien civilizations likely. Our Milky Way alone contains over 100 billion stars. If just a tiny fraction of those stars host habitable planets, and if just a few of those planets developed life, some of that life should have advanced enough to colonize the galaxy, or at least send signals we could detect. But so far, we have heard nothing. Consider the numbers. The galaxy is about 100,000 light-years across. Even traveling at a fraction of the speed of light, a civilization with advanced technology could, in theory, spread across the Milky Way in a few million years, a blink of an eye on cosmic timescales. If intelligent life is common, the galaxy should be teeming with evidence. Alien probes, radio signals, or even megastructures harnessing the energy of stars. Instead, the universe seems eerily quiet. This silence is what makes the Fermi paradox so unsettling. It suggests that either we are alone, or something is preventing intelligent life from spreading. One possible explanation is that life itself is rare. Perhaps the emergence of life requires an improbable combination of circumstances, making Earth an extraordinary exception. Even if microbial life is common, the leap from single-celled organisms to complex, intelligent beings might be vanishingly unlikely. This idea is known as the rare Earth hypothesis. It suggests that we may inhabit one of the few, or even the only, worlds where evolution stumbled upon consciousness. Alternatively, life may be common, but intelligence may not be. Evolution does not have foresight. It favors traits that ensure survival and reproduction, not necessarily traits that lead to spacefaring civilizations. Dinosaurs ruled the Earth for 165 million years without ever building radio telescopes. Intelligence, in this view, may be an evolutionary fluke, a fragile, unlikely outcome. Another possibility is that intelligent civilizations tend to destroy themselves. This is known as the Great Filter Hypothesis. Perhaps there is a barrier, a filter, that most life cannot pass. This filter could lie in the past, in the difficulty of life arising or developing intelligence. But if the filter lies ahead of us, the implications are even more disturbing. It could mean that technological civilizations inevitably self-destruct through nuclear war, environmental collapse, artificial intelligence, or some unforeseen catastrophe. In this scenario, the galaxy may be filled with the ruins of civilizations that burned brightly and then vanished. Some thinkers propose a more hopeful possibility. Alien civilizations exist, but they are avoiding us. This is the zoo hypothesis. Perhaps advanced beings are deliberately shielding us from their presence, waiting for humanity to reach a certain level of maturity before making contact. To us, the universe appears silent, but in reality, we are being observed like animals in a cosmic zoo. Others suggest we may be immersed in a simulation, our reality carefully constructed to appear empty of other intelligent life. The limits of our technology also offer a possible answer. We have only been searching for alien signals for a few decades, a tiny sliver of cosmic time. Our radio telescopes scan narrow portions of the sky and frequency bands. Civilizations may communicate in ways we cannot detect using technologies beyond our imagination. They might send signals that are fleeting or directed away from Earth. Or they may simply not be trying to communicate at all. Then there is the possibility that intelligent life is already here, but we are unable to recognize it. Perhaps alien probes lurk in our solar system, camouflaged or dormant. Or perhaps extraterrestrials are so different from us, so alien in form and thought, that we would not recognize them even if they were before our eyes. As science fiction author Arthur C. Clarke wrote, "Any sufficiently advanced technology is indistinguishable from magic." The Fermi paradox forces us to confront profound questions about our place in the cosmos. Are we the first intelligent civilization in the galaxy? If so, we bear a tremendous responsibility. As the lone torchbearers of consciousness, it falls on us to preserve and spread life. Or are we the latecomers, arriving after countless civilizations have risen and fallen? If that is the case, what fate befell them? And will we share their destiny? This mystery also shapes our search for life. Projects like SETI, the search for extraterrestrial intelligence, scan the heavens for radio signals. Space telescopes hunt for exoplanets in habitable zones. Missions to Mars and Europa search for microbial life. Each discovery brings us closer to an answer. And yet, as we peer deeper into the universe, the silence grows louder. Perhaps the most haunting possibility is that the universe is indeed empty. We are alone, adrift in an ocean of stars with no other voices to call back. This solitude is both terrifying and awe-inspiring. It means that consciousness, this spark of awareness we carry, is rare and precious. In the vast darkness, we may be the only witnesses to the universe's beauty and mystery. Or perhaps the silence is temporary. Somewhere out there, in the distant reaches of space, another intelligence may be looking up at its own night sky, asking the same question: where is everybody? The origin of life. Life is everywhere on Earth. From the deepest ocean trenches to the highest mountain peaks, living organisms flourish in astonishing variety. Yet the question of how life began remains one of the greatest unsolved mysteries in science. How did simple, non-living molecules give rise to the first living cells? How did chemistry turn into biology? This puzzle, the origin of life, haunts scientists and philosophers alike because it forces us to confront the boundary between the inanimate and the animate, between matter and meaning. To understand the mystery, consider the conditions of early Earth. Around 4 billion years ago, our planet was a hostile place. Volcanoes spewed lava and toxic gases, meteorites bombarded the surface, and the oceans churned with a primordial chemical soup. Somewhere in this chaotic environment, something extraordinary happened. Simple molecules assembled into more complex structures, amino acids, nucleotides, lipids, and eventually formed the first self-replicating systems. These systems crossed an invisible threshold, transitioning from non-living to living. But how? That is the question we still cannot answer. One of the earliest theories about life's origins was proposed in the 1920s by Russian biochemist Alexander Oparin and British scientist J.B.S. Haldane. They suggested that Earth's early atmosphere, rich in methane, ammonia, and water vapor, could have provided the right conditions for organic molecules to form spontaneously. Energy sources like lightning or ultraviolet radiation might have powered chemical reactions that produced the building blocks of life. This idea became known as the primordial soup hypothesis, and it inspired one of the most famous experiments in biology. In 1953, Stanley Miller and Harold Urey tested this idea by recreating early Earth conditions in the lab. They filled a glass flask with water and gases thought to be present on primitive Earth, then zapped it with electrical sparks to simulate lightning. Within days, they detected amino acids, the building blocks of proteins, forming in their flask. This groundbreaking result showed that complex organic molecules could emerge from simple chemicals under the right conditions. It was an exhilarating clue, but it was only the beginning. The problem is that life requires more than amino acids. Proteins, DNA, and cell membranes must work together in intricate harmony. Somehow, the first life had to store information, replicate itself, and carry out metabolism. Scientists wonder which came first, metabolism, replication, or cell structure. This has led to competing theories, each trying to explain how life took its first steps. One idea is the metabolism first hypothesis. It suggests that networks of chemical reactions formed self-sustaining cycles, like tiny factories that concentrated energy in matter. Over time, these cycles may have become more complex, eventually giving rise to life. This idea focuses on the chemical energy flows that are the heartbeat of all living systems. But critics argue that without a way to store information, such systems could not evolve. Another theory is the replication first model, centered on RNA. RNA, a cousin of DNA, can both store genetic information and act as a catalyst for chemical reactions. Some scientists propose that life began in an RNA world, where self-replicating RNA molecules evolved before proteins and DNA. Experiments have shown that RNA can, under certain conditions, assemble spontaneously and even copy itself. But there are hurdles. RNA is fragile and breaks down easily. How did such a delicate molecule survive in the harsh environment of early Earth? Then there is the question of cell membranes. Modern cells are enclosed by lipid bilayers, thin films of fatty molecules that create a boundary between the inside and outside. Without such membranes, life's chemistry would spill into the environment. Could simple lipids have formed bubbles in the primordial ocean, trapping molecules and creating tiny compartments? Experiments suggest this is possible. These protocells might have provided a safe haven for RNA and metabolic reactions to flourish. Beyond Earth, some scientists look to the stars for answers. The theory of panspermia suggests that life's building blocks, or even life itself, came from space, carried on comets or meteorites. Organic molecules have been detected in interstellar clouds and meteorites, hinting that the ingredients for life may be widespread in the cosmos. But panspermia only shifts the mystery elsewhere. Even if life came from space, how did it start? Some researchers propose more exotic scenarios. Hydrothermal vents on the ocean floor, with their rich chemistry and energy flows, might have been cradles of life. In these dark, high-pressure environments, mineral-rich fluids gush from the Earth's crust, creating natural laboratories for chemical reactions. Could these vents have nurtured the first life forms? Others point to shallow pools, where cycles of wetting and drying might have concentrated molecules and powered polymer formation. Despite decades of research, no single theory has yet provided a complete answer. The transition from chemistry to biology may have been a gradual process, with no sharp dividing line between life and non-life. Perhaps there were many failed experiments by nature, countless molecular assemblies that almost achieved life but fell short. Only one lineage succeeded, leading to all the diversity we see today. The origin of life is not just a scientific puzzle. It's a philosophical one. What does it mean to be alive? At what point does a collection of molecules become living? Is life an inevitable outcome of chemistry, or is it a rare fluke in a vast, indifferent universe? If we could understand how life began, it would not only reveal our own origins, but also help us search for life elsewhere. On Mars, Europa, or Enceladus, there may be echoes of the same processes that played out on early Earth. For now, the mystery remains unsolved. Life arose from non-life once, at least on Earth. Could it happen again? Or is there something unique and unrepeatable about that moment 4 billion years ago? Until we find the answer, we live with the haunting realization that the line between matter and meaning, between dust and desire, is thinner than we ever imagined. The brain's memory storage. The human brain is the most complex structure in the known universe. Weighing just over 3 pounds, it is a dense network of roughly 86 billion neurons, connected by trillions of synapses. This intricate web somehow gives rise to thought, perception, emotion, and memory. Memory is what stitches together the moments of our lives into a coherent whole. It allows us to learn, to plan, and to maintain a sense of self. And yet, despite decades of neuroscience, we still do not fully understand where and how the brain stores memories. Is memory like a computer hard drive, with precise locations for every piece of information? Or is it something far stranger, woven into the very fabric of consciousness? For centuries, philosophers and scientists have pondered the nature of memory. In ancient Greece, Plato imagined the mind as a wax tablet on which experiences left their impressions. Later, in the 20th century, with the rise of computers, memory was often compared to data storage. This analogy suggested that memories are encoded, filed away, and retrieved as needed. But the brain is not a computer. Its architecture and operations are radically different, and this makes the puzzle of memory even more mysterious. Modern neuroscience has revealed some pieces of the puzzle. We know that memories are not stored in a single location, like files in a cabinet. Instead, they are distributed across networks of neurons. When you recall your first day of school, different aspects of that memory, sounds, sights, emotions, activate different regions of the brain. The hippocampus, a seahorse-shaped structure deep within the brain, plays a key role in forming new memories. Damage to the hippocampus can leave a person unable to create new long-term memories, a condition famously illustrated in the case of patient HM, whose hippocampi were removed to treat epilepsy. Yet even without hippocampi, HM retained older memories and could still learn certain motor skills. This suggests that memories, once formed, are gradually transferred and consolidated in other brain regions. But where, exactly, are these memories stored? One hypothesis is that memories are encoded in patterns of connections between neurons. When we experience something new, synapses, The tiny gaps between neurons are strengthened or weakened. This process, known as synaptic plasticity, is thought to be a key mechanism for memory storage. The saying "neurons that fire together, wire together" captures this idea. Repeated activity creates lasting changes in neural circuits. Long-term potentiation, discovered in the 1970s, is one such mechanism in which synaptic connections become stronger with repeated use. Yet this theory raises perplexing questions. If memories are stored in synapses, how do they survive the constant turnover of the brain's molecules? Proteins and other cellular components are continually broken down and replaced. In a matter of weeks or months, the physical structure of a synapse might be entirely renewed. How, then, can a memory persist for decades? Does the brain somehow preserve the pattern of connections even as the materials change? Or is memory stored in a deeper, more durable way? Some researchers have proposed that memories might not reside solely in synaptic changes. Perhaps they are encoded in the very structure of neurons, such as the patterns of dendritic spines, or even in molecular marks on DNA and proteins, epigenetic modifications that influence gene expression. Others speculate about engram cells, special groups of neurons that store specific memories. Experiments in mice have shown that activating certain engram cells can trigger recall of specific experiences, suggesting memories are encoded in ensembles of neurons. There are even stranger possibilities. Could memories be stored holographically, distributed across the brain like information in a hologram? In a holographic system, even a small fragment contains information about the whole, though in lower resolution. This idea might explain why damage to one part of the brain often degrades memory rather than erasing it entirely. The brain's remarkable resilience, its ability to function even when partially injured, hints at a distributed, redundant memory system. Some scientists have considered quantum effects in the brain, though these ideas remain speculative. Could memory storage involve quantum coherence, entangling information in ways we don't yet understand? If so, the brain's memory system might operate at levels of complexity far beyond our current models. What makes the mystery even deeper is that memory is not static. Each time we recall a memory, we alter it. Neuroscience shows that memories are reconstructed, not replayed like a video. When you remember your first day of school, your brain pieces together fragments from various regions, influenced by your current emotions and beliefs. In this way, memories are more like living stories than fixed records. This plasticity allows us to learn and adapt, but it also means memories can be fragile and unreliable. The brain's storage capacity is another marvel. Estimates suggest that the human brain could hold the equivalent of hundreds of terabytes of information. Yet it does this with astonishing efficiency, using networks of neurons that multitask and overlap. Unlike a computer, which stores files in discrete sectors, the brain's memory system is dynamic and interconnected, blurring the line between storage and processing. Despite these insights, the full picture remains elusive. Memory is not just a scientific problem. It touches the deepest aspects of our humanity. Memories define who we are. They give us identity, connect us to others, and shape our perception of reality. To understand memory is to understand the self. But if we still don't know where memories truly reside, what does that say about the nature of the mind? Are we like the ship of Theseus, continually rebuilt yet somehow the same? Perhaps the brain's memory storage is not like a hard drive at all. Perhaps it is more like a river, ever-changing, flowing, yet somehow maintaining continuity. As science probes deeper into the brain, we may discover answers, or we may find that the mystery of memory is inseparable from the mystery of consciousness itself. Quantum entanglement. In the strange and counterintuitive world of quantum physics, there is perhaps no phenomenon more mysterious or more unsettling than quantum entanglement. It is a process where two particles become linked in such a way that the state of one instantly determines the state of the other. no matter how far apart they are. Measure one particle here on Earth, and the other, on the far side of the galaxy, will seem to know what has happened. This instantaneous connection appears to defy the cosmic speed limit set by Einstein's theory of relativity, which insists that nothing, not even information, can travel faster than the speed of light. It was this apparent contradiction that led Einstein to dismiss entanglement as spooky action at a distance. But modern experiments have confirmed that entanglement is real, forcing us to rethink our most basic assumptions about the universe. To grasp why entanglement is so strange, consider two particles, electrons for example, that interact and become entangled. From that moment on, their properties are no longer independent. Their spins, positions, or other quantum states become intertwined. If you measure the spin of one electron and find it pointing up, you instantly know the spin of the other electron will be down, even if it is light years away. This isn't just a matter of incomplete information. Quantum mechanics suggests that until you measure the spin, neither electron has a definite spin at all. Instead, they exist in a superposition, a blend of possibilities. The act of measurement collapses this superposition, and somehow the other electron state collapses simultaneously. Einstein found this deeply troubling. In 1935, along with Boris Podolsky and Nathan Rosen, he published a paper outlining what became known as the EPR paradox. They argued that if quantum mechanics allowed such instantaneous correlations, it must be incomplete. There had to be hidden variables, unknown factors that determine the outcomes in advance. Otherwise, information would have to travel faster than light, violating relativity. For decades, this question lingered. Was quantum mechanics truly describing reality, or was it just a statistical tool covering up a deeper, deterministic layer? The answer came in the 1960s, when physicist John Bell devised a way to test the idea of hidden variables. Bell's theorem showed that if hidden variables existed, certain correlations between entangled particles would have to obey strict limits. Quantum mechanics predicted stronger correlations, violations of Bell's inequalities. In the 1980s and beyond, a series of ingenious experiments tested these predictions. The results were clear. Entangled particles exhibit correlations that cannot be explained by any local hidden variables. Quantum mechanics was right. Entanglement was real. Einstein's spooky action could not be dismissed. But what does this mean for our understanding of reality? The first thing to note is that entanglement does not allow faster-than-light communication. You cannot use it to send messages instantly across space. When you measure one particle, you get a random result. Only when you compare it with the measurement of the other particle do the correlations appear. The universe preserves causality, but at a price. It seems to permit non-local connections that defy our everyday intuitions about space and time. Some physicists interpret entanglement as evidence that the universe is deeply interconnected in ways we don't yet understand. In the standard Copenhagen interpretation of quantum mechanics, the wave function, the mathematical description of a system, collapses instantaneously when measured, binding entangled particles no matter the distance. But in other interpretations, the story changes. The many worlds interpretation suggests that all possible outcomes happen in branching parallel universes. There is no spooky action, only a splitting of realities where each measurement result is realized. In this view, entanglement is a reflection of the underlying multiverse. Even more radical are ideas that space itself might emerge from entanglement. Some physicists speculate that the fabric of space-time is woven together by quantum entanglement. If so, entanglement isn't just a feature of particles, it's the fundamental thread of reality. This idea, known as A equals EPR, proposes a link between entanglement and Einstein-Rosen bridges, wormholes in spacetime. Could entangled particles be connected by microscopic wormholes outside our perception? Entanglement also lies at the heart of quantum technologies. Quantum computers exploit entanglement to perform calculations that would be impossible for classical computers. Quantum cryptography uses entangled particles to create unbreakable encryption keys. Quantum teleportation, which sounds like science fiction, allows the quantum state of a particle to be transmitted from one place to another using entanglement, though the particle itself is not transported, only its information. Yet the deeper philosophical implications remain unresolved. Does entanglement mean that reality is non-local, that there are no true boundaries in space? Or does it suggest that our notions of causality and independence are illusions, artifacts of a limited perspective? Some have even wondered whether consciousness itself might involve quantum entanglement, though such ideas remain speculative. The mystery of entanglement forces us to confront a universe that is far stranger than we imagined. Particles separated by vast distances act as if they are part of a single system, bound by invisible threads. Our classical intuition tells us this shouldn't happen, but the quantum world doesn't care about our intuitions. It follows its own logic, a logic that seems to blur the distinction between here and there, between this and that. Einstein was right to call it spooky. Entanglement defies easy explanation and challenges our deepest assumptions about reality. Yet, it is also a window into the profound interconnectedness of the cosmos. In a universe built from quantum fabric, perhaps nothing is truly separate. Perhaps everything is entangled. A cause of fast radio bursts. In the vast darkness of space, a strange and fleeting phenomenon has captured the attention of astronomers. Fast radio bursts, or FRBs. These are incredibly brief, yet powerful pulses of radio waves that seem to arrive from random points in the cosmos. Lasting only a few milliseconds, barely the blink of an eye, each burst releases more energy than the sun emits in an entire day. First discovered in 2007, FRBs have remained one of the greatest unsolved mysteries in modern astronomy. What could produce such intense, short-lived flashes of energy? Are they natural cosmic events, or could they hint at something far more exotic? The story of FRBs began when astronomers were sifting through data from the Parkes Observatory in Australia. They stumbled upon a curious signal, later dubbed the Lorimer burst after its discoverer. At first, some suspected a technical glitch, but repeated detections confirmed these signals were real, and they were coming from outside our galaxy. As more telescopes joined the search, astronomers began detecting dozens, then hundreds, of these mysterious bursts. Some appeared to occur only once, while others repeated from the same location, deepening the mystery. What makes FRBs so puzzling is their combination of extreme power and brevity. To create such a burst, something must release an enormous amount of energy in an incredibly short time. But how? One leading theory points to magnetars, neutron stars with magnetic fields a trillion times stronger than Earth's. When a magnetar's magnetic field twists and snaps, it could unleash a burst of energy powerful enough to produce an FRB. In 2020, astronomers observed an FRB-like signal from a magnetar within our own Milky Way, lending support to this idea. But while magnetars may explain some FRBs, they might not account for all of them. Another possibility is that FRBs come from collisions between dense objects, such as neutron stars or black holes. When two neutron stars spiral into each other and merge, they release intense gravitational waves and could, in theory, emit powerful radio bursts as well. Such events would be rare and non-repeating, potentially explaining the one-off FRBs that never flash again. But this hypothesis struggles to explain the repeating FRBs, which seem to pulse over and over from the same source. Some scientists have proposed more exotic origins. Could FRBs be powered by alien technology? A few researchers have speculated that the bursts might be artificial signals, perhaps energy beams used to power spacecraft across interstellar distances. This idea is purely speculative and lacks direct evidence, but it highlights how FRBs force us to think beyond conventional astrophysics. If they were artificial, they would represent a cosmic lighthouse, an intentional or unintentional message from intelligent life. Most scientists remain cautious about such claims, preferring natural explanations until proven otherwise. Adding to the mystery is the way FRBs travel through space. As radio waves journey across billions of light years, they pass through clouds of ionized gas, which scatter and slow the signals in characteristic ways. By analyzing this dispersion, astronomers can estimate how far an FRB has traveled. Some bursts come from distant galaxies, suggesting they originated when the universe was much younger. Others are closer, hinting at a wide variety of sources. Recently, telescopes like CHIME in Canada have begun detecting hundreds of FRBs, including some that repeat in regular patterns, as if following a cosmic heartbeat. Why do some FRBs repeat while others don't? This is one of the key puzzles. Repeating FRBs may come from systems where an energy source is stable, like a young magnetar or a neutron star orbiting another star. Non-repeating FRBs might instead signal cataclysmic events, once-in-a-lifetime cosmic explosions that destroy their source. Or perhaps there are multiple types of FRBs, each with its own origin. To unravel the mystery, astronomers are deploying powerful new instruments. The CHIME telescope has revolutionized the field, detecting thousands of FRBs and helping map their distribution across the sky. Meanwhile, facilities like the Very Large Array in FAST in China are pinpointing FRB locations with increasing precision. By identifying the galaxies that host FRBs, researchers hope to learn more about the environments that give rise to them. Still, fundamental questions remain. How can something as small as a neutron star produce a signal detectable across billions of light years? Why are FRBs so much more common than we expected? And are we seeing only the tip of the iceberg, just a fraction of a much larger population of cosmic radio bursts? Some theorists believe FRBs might even offer insights into the nature of space and time. As radio waves traverse the universe, they interact with intergalactic matter, potentially revealing hidden properties of the cosmos. By studying FRBs, we may learn more about dark matter, magnetic fields in space, or even exotic particles that we cannot detect otherwise. The mystery of FRBs is haunting because it reminds us how little we know about the universe. Somewhere out there, powerful engines are firing off millisecond-long bursts of energy, yet we still don't know what they are or why they exist. Are they natural phenomena, rare and fleeting? Or are they signals of something more profound, perhaps even a message waiting to be decoded? For now, the universe remains silent except for these sudden, enigmatic flashes. They come without warning, whisper across the void, and vanish before we can grasp their meaning. Whatever their source, FRBs invite us to listen carefully to the cosmos. Somewhere in the static, an answer may be waiting. The nature of time rules our lives. We wake up, grow old, remember the past, and anticipate the future. Events unfold in a single direction. Eggs break, but never unbreak. Smoke rises, but never returns to the match. And memories are always of what has been, not what will be. This one-way flow of time, what physicists call the arrow of time, feels so deeply woven into our experience that we rarely question it. And yet, when scientists study the fundamental laws of nature, they find something startling. Those laws don't seem to care about direction. In the equations that govern the motion of particles, the past and the future are treated the same. This disconnect between our experience and the mathematics has left physicists with a profound and unsettling mystery. Why does time flow forward? And is that flow real or just an illusion? The concept of time has fascinated thinkers for millennia. Ancient philosophers imagined time as a river, always moving forward. In the 17th century, Isaac Newton described time as absolute, a ticking clock that exists independently of anything else, marching forward uniformly across the universe. But this view was appended in the early 20th century by Albert Einstein. In his theory of relativity, time is not separate from space. Instead, the two are woven together into a single fabric, space-time. Time slows down near massive objects or when traveling close to the speed of light. It is no longer absolute. And yet, even in Einstein's equations, time can run forward or backward without contradiction. The laws still work perfectly in either direction. So where does the arrow of time come from? One leading explanation points to entropy, a measure of disorder. According to the second law of thermodynamics, the entropy of a closed system will tend to increase over time. Ice melts, paper burns, and buildings crumble. In each case, disorder rises, and these processes are effectively irreversible. You never see melted ice spontaneously refreeze. This increase in entropy gives time its direction. It provides a before and an after. But here is the catch. The laws of physics that govern individual particles tend to require entropy to increase. On the scale of atoms and molecules, processes are reversible. If you could track every particle in a cloud of smoke, you could, in theory, run the tape backward and watch the smoke reassemble into a match. So why don't we see that happen? The answer seems to lie in probabilities. There are far more disordered states than ordered ones. While it's not impossible for particles to rearrange themselves into a tidy configuration, it's so improbable that we never see it. Entropy increases not because it must, but because it's overwhelmingly likely. This explanation satisfies many physicists, but it raises a deeper question. Why was the universe so ordered to begin with? At the moment of the Big Bang, the universe had incredibly low entropy. It was smooth, uniform, and filled with potential. If time's arrow comes from entropy, then the mystery of time's direction becomes the mystery of the universe's initial condition. Why did it begin in such a special, low entropy state? Some theories suggest that time's arrow is a consequence of cosmic expansion. As the universe grows, it creates room for entropy to increase. Others propose that time might be symmetric after all, but we are trapped in one direction because of how our brains process information. We remember the past, not the future, because our mental states rely on the buildup of entropy. In this view, the arrow of time is not an external reality. It's a feature of our biology, a trick of perception shaped by thermodynamic processes. There are even models of the universe where time runs in both directions. In these Janus cosmologies, time flows outward from a central low entropy state in two symmetrical directions. In one direction, time flows forward as we experience it. In the other, it flows backward from our point of view. From a timeless perspective, both directions are equally valid. But observers in each branch would perceive their own arrow of time, unaware of the opposite flow on the other side. Quantum mechanics adds yet another layer of complexity. In quantum theory, particles exist in a blur of probabilities until observed, at which point the wave function collapses into a definite outcome. Some interpretations, like the Copenhagen view, suggest that this collapse introduces an element of irreversibility and therefore time's direction. But others, like the many worlds interpretation, reject collapse altogether. In that view, every possible outcome occurs in a branching multiverse. The equations remain time-symmetric. Again, it seems the arrow of time may not be written into the fabric of reality, but into the way we experience it. Still, we cannot ignore the visceral truth. Time feels real. It moves. It flows. It separates what was from what is and what will be. This feeling may be an illusion, but it shapes our existence. Without time, there would be no causality, no memory, no evolution, no meaning. Some physicists, like Carlo Rovelli, argue that time may not even exist at the deepest level of reality. In certain quantum gravity theories, time disappears entirely from the equations. What we perceive as time might emerge only at macroscopic scales as a byproduct of complexity. This view is both humbling and disorienting. If time is not fundamental, then the story of the universe may be a static tapestry, with every moment already existing, past, present, and future laid out like pages in a book. Our experience of moving through time could be like flipping through those pages, moment by moment. In this block universe view, time doesn't flow. It simply is. The future already exists, just as the past does. But we, as conscious beings, move through it, giving it the illusion of motion. So why does time seem to flow forward? Perhaps it's entropy. Perhaps it's our biology. Perhaps it's a feature of consciousness interacting with a timeless universe. Or perhaps we're asking the wrong question altogether. The arrow of time may not be something that exists out there, but something that emerges from the way information, matter, and energy interact. It may not be absolute, but relational, dependent on perspective, scale, and context. Until we unravel the full nature of time, we remain caught in its current. It pulls us forward through birth and death, through memory and hope. Whether real or illusory, it defines the shape of our lives. Time, as we know it, may be a shadow on the wall of a deeper, timeless reality, one we have only begun to glimpse. The placebo effect. The human mind is a powerful thing. It can imagine futures, replay the past, and even change the way the body works in the present. Perhaps nothing illustrates this more vividly than the placebo effect, a strange and fascinating phenomenon in which people experience real healing from treatments that are, in fact, fake. Sugar pills, saline injections, sham surgeries, all can produce genuine improvements in health when the patient believes they are receiving real medicine. Sometimes the results are so dramatic that they rival the effects of actual drugs. But how is this possible? How can belief alone alter the biology of the body? This is a mystery that continues to puzzle scientists and challenges our understanding of the connection between mind and matter. The placebo effect has been known for centuries, though it wasn't always recognized as such. In ancient times, healers would administer rituals and potions with no real therapeutic ingredients, yet patients often reported relief. It wasn't until modern medicine developed rigorous clinical trials that the power of placebo became impossible to ignore. In these trials, patients are often divided into two groups. One receives the experimental drug, and the other receives a lookalike pill containing no active substance. Repeatedly, researchers noticed that people in the placebo group also improved, sometimes in significant ways. Pain diminished, symptoms subsided. Even measurable biological markers, like heart rate or hormone levels, changed. At first, doctors viewed this as a nuisance, something to control for in experiments. But over time, it became clear that the placebo effect is not mere imagination. It's not patients faking improvement. Brain scans have shown that placebos can trigger real changes in brain chemistry. For instance, when a patient believes they're receiving a painkiller, the brain releases endorphins, natural opioids that reduce pain. In some cases, these effects can be blocked by drugs that interfere with opioid pathways, proving that the placebo is acting through biological mechanisms. This raises a profound question. What exactly is happening in the body during a placebo response? One clue lies in expectation. When we expect to get better, the brain sends signals to various systems, the immune system, the nervous system, even the endocrine system, that prepare the body for healing. This expectation can influence how we perceive symptoms, modulate stress responses, and alter inflammatory processes. Belief, it seems, acts as a kind of internal medicine, tuning the body's systems in ways we're only beginning to understand. But the placebo effect is not limited to subjective symptoms like pain or mood. Studies have found placebo effects in conditions as diverse as Parkinson's disease, asthma, and even immune disorders. In Parkinson's patients, placebo treatments have been shown to increase dopamine release in the brain, temporarily improving motor function. In people with asthma, inhaling a placebo can make them feel less short of breath, even if lung function tests show no change. In immune disorders, belief in treatment can sometimes modulate antibody production. These findings suggest that the placebo effect taps into deep and complex biological pathways. Stranger still is the phenomenon of sham surgery. In some studies, patients with knee pain were divided into two groups. One received actual surgery, while the other underwent a fake procedure in which doctors made an incision but did nothing further. Astonishingly, patients in both groups reported similar improvements. This suggests that the ritual of surgery, the lights, the anesthesia, the surgeon's confidence, can trigger powerful healing responses, independent of any physical intervention. Even more intriguing is the open-label placebo. Here, patients are told explicitly that they are receiving a placebo, yet they still experience improvements. This suggests that the effect isn't solely about being deceived. It may involve the therapeutic context, the act of being cared for, the meaning attached to treatment, and the symbolic power of medical rituals. Healing, it seems, is as much about the mind as it is about molecules. So why does the placebo effect work at all? Evolutionary biologists speculate that it may have roots in the body's ability to prepare for healing in supportive environments. When we feel safe and cared for, our bodies shift into a state where repair and recovery are prioritized. In contrast, stress and fear can trigger fight or flight responses that suppress healing. The placebo effect might be a byproduct of this ancient mind-body connection. The placebo effect also has a darker twin, the nocebo effect. Just as positive expectations can heal, negative expectations can harm. If a patient believes a harmless pill will cause side effects, they may experience nausea, headaches, or worse. This demonstrates how the mind can influence not only healing, but suffering as well. Despite its power, the placebo effect is not a cure-all. It doesn't shrink tumors or eradicate infections. It works best for symptoms the brain can modulate: pain, fatigue, depression, and certain functional disorders. Yet understanding how it works could revolutionize medicine. If we can harness the placebo effect deliberately, we might amplify the effectiveness of treatments and reduce reliance on drugs with harmful side effects. This mystery forces us to confront the blurry line between mind and body. In the mechanistic model of medicine, the body is treated as a machine, and healing comes from external interventions, drugs, surgeries, devices. But the placebo effect suggests that healing also comes from within, shaped by thoughts, emotions, and beliefs. It invites us to see medicine not only as a science, but as an art, an interplay of biology, psychology, and meaning. For now, the placebo effect remains a paradox. It is real, measurable, and yet rooted in something as intangible as belief. It challenges our notions of what is active in healing and what is inert. And it reminds us that the mind is not just a passive observer of the body as processes, but an active participant in health and disease. Perhaps the most remarkable lesson of the placebo effect is that we are more powerful than we imagine. Within us lies the capacity to influence our own biology, not with magic, but with belief, trust, and expectation. And that capacity, though mysterious, might be one of the most ancient and universal medicines of all. The Pioneer Anomaly. In the early 1970s, NASA launched two spacecraft, Pioneer 10 and Pioneer 11, on historic journeys to explore the outer reaches of our solar system. These were among humanity's first emissaries to the stars, carrying golden plaques in case they were ever found by intelligent life. As the decades passed, the Pioneer probes traveled further than any spacecraft had before, venturing beyond the orbits of the outer planets and into the vast darkness of interstellar space. But as scientists tracked their progress, they noticed something strange. Both spacecraft seemed to be slowing down ever so slightly, as if some mysterious force were tugging at them from behind. This subtle but persistent deceleration became known as the Pioneer anomaly, and for years it raised an unsettling question. Was this a simple error in our understanding, or evidence of unknown forces at work in the cosmos? The anomaly was first noticed in the 1980s, as NASA tracked radio signals sent to and from the Pioneers. Using the Doppler effect, the way radio waves shift frequency depending on motion, engineers could measure the spacecraft's speeds with incredible precision. But the data didn't line up with predictions. Pioneer 10 and 11 were slowing down slightly more than expected as they moved away from the Sun. The effect was tiny, about 8.7 nanometers per second squared, but consistent. Over time, this small deviation added up, causing the spacecraft to lag behind their projected trajectories. At first, scientists wondered if the anomaly was due to gravitational tugs from unseen objects, perhaps distant asteroids, or even hypothetical Planet X lurking in the outer solar system. Others speculated that dark matter or modifications to gravity itself might be responsible. Could Newton's and Einstein's laws break down over vast distances? Or was there some entirely new physics waiting to be discovered? The possibility of new physics was thrilling. If gravity behaved differently at the edge of the solar system, it could hint at phenomena like modified Newtonian dynamics, or even connections to the elusive dark energy driving the expansion of the universe. Some researchers imagined exotic explanations, unseen forces, interstellar drag, or even signals from alien civilizations trying to slow the probes. But before jumping to such extraordinary conclusions, scientists had to exhaust more mundane possibilities. One leading hypothesis was that the spacecraft themselves were responsible for the anomaly. As Pioneer 10 and 11 traveled through space, they carried radioactive power sources, small nuclear batteries called RTGs, that generated heat. Could this heat, radiating unevenly from the spacecraft, act like a tiny thruster, pushing them ever so slightly off course? In other words, was the anomaly not a pull from space, but a push from the probes themselves? This idea led to painstaking work. Engineers dug through decades-old mission data, blueprints, and telemetry logs to build detailed computer models of the spacecraft's behavior. They considered every possible source of heat and radiation, electrical systems, the RTGs, and even sunlight reflecting off antennas. After years of analysis, their models suggested that anisotropic thermal radiation, heat radiating more strongly in one direction, could account for the anomalous deceleration. Essentially, the probes were emitting photons preferentially in one direction, creating a tiny but constant recoil effect. By 2012, most scientists agreed that this thermal recoil explained the Pioneer anomaly. It wasn't new physics or alien forces. It was heat. The mystery, it seemed, had been solved. Yet even in resolution, the anomaly remains fascinating. For one, it highlights the extraordinary precision of modern science. To even detect such a subtle effect required measuring distances and speeds over billions of kilometers, with accuracy far beyond what the mission's designers imagined in the 1970s. It also demonstrates how careful scientists must be in distinguishing genuine mysteries from the complex behavior of machines and environments. But not everyone is satisfied. A few researchers argue that thermal recoil may not account for the entire anomaly, or that other forces could still be at play in the outer solar system. Could there be tiny errors in our models of gravity? Could dark matter interact with spacecraft in unexpected ways? Or is the universe reminding us, once again, how easy it is to overestimate our knowledge? The Pioneer anomaly lingers in our imagination because it touches on something profound, the limits of human understanding. For a moment, it seemed that two aging spacecraft, drifting silently through the void, had uncovered cracks in the foundation of physics. Even now, as the probes speed further into interstellar space, they remind us of how small we are in the cosmos and how much we still have to learn. Perhaps in the end, the anomaly is not a testament to unknown forces, but to the tenacity of human curiosity. It shows that even the smallest deviations can spark big questions. And it reminds us that mysteries, whether solved or not, are what drive us to explore. Ultra-high energy cosmic rays, high above our heads, the universe is alive with invisible activity. From the depths of space, particles rain down on Earth every second, moving so fast they carry energies beyond anything we can create on Earth. These are cosmic rays, tiny subatomic bullets, mostly protons, traveling at near the speed of light. Most cosmic rays are relatively low in energy, streaming gently from the sun or exploding stars. But then there are the rarer and mysterious few, the ultra-high energy cosmic rays. These particles strike our planet with unimaginable force, carrying energies millions of times greater than anything produced in our most powerful particle accelerators. And we don't know where they come from, or how the universe could possibly accelerate something so small to such titanic speeds. The first clue to this mystery came in 1912, when physicist Victor Hess carried an electroscope high into the atmosphere in a hot air balloon. He discovered that radiation increased with altitude, proving it was coming from space, not the Earth. Later, scientists began to study these cosmic rays in detail. Most were found to have modest energies, born in familiar astrophysical events like supernova. But in 1962, something astonishing happened. A detector in New Mexico recorded a cosmic ray so powerful it defied belief. This single subatomic particle, no bigger than a proton, carried the same energy as a fast-pitched baseball. For a particle, that's an almost incomprehensible amount of energy. Since then, detectors around the world have caught other ultra-high energy cosmic rays, though they remain rare, maybe 1 per square kilometer per century. These rare visitors are so energetic, they are barely deflected by the magnetic fields of galaxies. They arrive at Earth on nearly straight paths, offering a tantalizing possibility. If we can trace their trajectories backward, we might discover their sources. But here's the problem. When we try, they don't point to anything obvious. No exploding star, no active galactic nucleus, no smoking gun. Just empty regions of space. How could the universe accelerate a particle to such speeds? Even our most powerful machines, like the Large Hadron Collider, pale in comparison. To reach these energies, you'd need a cosmic accelerator on a scale beyond anything we've ever imagined. One idea is that these particles are launched by active galactic nuclei, supermassive black holes at the centers of galaxies, surrounded by swirling disks of matter and enormous magnetic fields. As matter falls into the black hole, it releases colossal amounts of energy, perhaps enough to fling protons across the universe at ultra-high speeds. Another candidate is gamma-ray bursts, the brightest explosions in the cosmos. In these catastrophic events, massive stars collapse or neutron stars merge, sending out powerful jets of energy. The shock waves from these jets might accelerate particles to incredible speeds. Magnetars, neutron stars with mind-bendingly strong magnetic fields, are also contenders. Their intense magnetic activity could act like a slingshot for charged particles. But even these cosmic powerhouses have limits. There's a theoretical boundary, called the Greisen-Zatzpin-Kuzmin limit, which suggests that ultra-high energy cosmic rays should lose energy as they travel through the universe. The reason? They collide with photons from the cosmic microwave background, the leftover glow of the Big Bang. These collisions should sap their energy long before they reach Earth. Yet we still detect them. Are they coming from nearby sources, so they don't have time to lose energy? Or is there something wrong with our understanding of physics at these extreme energies? Some scientists have speculated about more exotic origins. Could ultra-high energy cosmic rays be fragments of decaying super-heavy particles created in the Big Bang? Or could they be evidence of entirely new physics, like interactions with dark matter, cosmic strings, or even the fabric of spacetime itself? If so, these tiny messengers might carry clues about the deepest structure of the universe. To study these elusive particles, scientists have built vast observatories, like the Pure Auger Observatory in Argentina. It covers an area the size of Rhode Island, with detectors spread across the plains to catch the rare air showers these particles produce. When an ultra-high energy cosmic ray hits Earth's atmosphere, it slams into molecules of air, creating a cascade of secondary particles that spread out over kilometers. By analyzing these showers, scientists can estimate the original particle's energy and arrival direction. Yet even with these tools, the mystery remains unsolved. The ultra-high energy cosmic rays we detect are rare, random, and stubbornly silent about their origins. They hint at processes more violent and powerful than anything we've ever witnessed. They suggest that somewhere in the universe, nature has built accelerators that make our most advanced machines look like toys. Perhaps one day we'll catch one in the act, see a cosmic particle burst forth from a distant black hole jet, or a gamma ray burst and trace it home. Until then, we can only listen for these whispers from the edge of physics, wondering what they're trying to tell us. Are they reminders of cosmic violence? Clues to undiscovered laws of nature? Or messages from a universe that is still far stranger than we can imagine? For now, ultra-high energy cosmic rays remain one of astronomy's greatest puzzles. Tiny particles carrying giant secrets, falling silently from the sky. Ball lightning. During a thunderstorm, the sky comes alive with power. Flashes of lightning split the clouds, and thunder rolls across the landscape. But every so often, rarely, and often fleetingly, witnesses report something even stranger. Glowing spheres of light drifting silently through the air. These luminous orbs, sometimes as small as a marble, and sometimes as large as a basketball, have been seen floating across fields, through open windows, and even inside houses. They are called ball lightning, and they remain one of nature's most enduring mysteries. For centuries, scientists and eyewitnesses alike have struggled to explain them. What are these glowing spheres? And why has no one been able to consistently create or study them in a laboratory? Accounts of ball lightning go back hundreds of years. In 1638, during a storm in Devon, England, a ball of fire reportedly entered a church, killing several people and damaging the building. Sailors on 18th century ships described glowing orbs dancing along the masts during storms. Even today, pilots sometimes report mysterious lights floating in storm clouds or near airplanes. Witnesses describe them as bright, glowing spheres that move erratically, sometimes passing through walls or windows, and then vanishing with a sudden pop, or even an explosion. These reports are eerily consistent, yet attempts to study ball lightning directly have proven frustratingly elusive. Part of the difficulty lies in its rarity and unpredictability. Unlike ordinary lightning, which is a well-understood discharge of electricity, ball lightning appears without warning and lasts only seconds. In modern times, many reports have been dismissed as optical illusions, after images from lightning flashes, or even hallucinations caused by stress or fear during storms. But the sheer number of similar accounts, often from experienced observers like pilots or sailors, suggests there is something real behind the phenomenon. In the 20th century, scientists began to take ball lightning seriously. Various theories emerged to explain it. One idea is that ball lightning is a kind of plasma, an ionized gas held together by electric and magnetic fields. In this model, a regular lightning strike might create conditions that trap hot, glowing plasma in a spherical shape. The problem is that plasma usually disperses quickly, whereas ball lightning can linger for several seconds or more. Other theories propose chemical origins. Perhaps lightning vaporizes certain materials on the ground, like silicon from soil, creating a floating, burning ball of charged particles. This might explain why some ball lightning has been observed near power lines or metal structures. In 2012, a team of Chinese scientists studying a thunderstorm accidentally captured what might have been ball lightning on video and spectrograph. Their data showed the glowing orb contained elements like silicon, iron, and calcium, hinting that vaporized materials from the ground could play a role. More exotic theories suggest ball lightning might involve microwaves. Some researchers propose that lightning strikes can create pockets of microwaves trapped in a plasma bubble, forming a kind of glowing, self-sustaining energy structure. In laboratories, scientists have managed to create small, glowing plasma balls using microwaves in certain gases. But these are not quite the same as the free-floating, long-lasting orbs people report during storms. Perhaps the strangest reports of ball lightning describe it moving through solid walls or glass without leaving a mark. These accounts have led to speculation about whether ball lightning is a purely physical phenomenon or partly a trick of perception. Could it be a complex interaction between real electrical phenomena and the brain's visual system? Or could it involve unknown states of matter or energy that behave differently from anything we've studied? The lack of reproducible laboratory experiments keeps ball lightning at the edge of scientific understanding. Researchers have recreated effects that look like ball lightning, but none have demonstrated a process that matches all of its reported behaviors. Until they do, we are left with scattered clues, rare videos, eyewitness accounts, and unexplained marks on walls and floors where glowing orbs allegedly touched down. Ball lightning fascinates us because it feels like a glimpse into another layer of reality, a phenomenon that seems almost alive, moving with strange intelligence and defying ordinary physics. Perhaps one day, with better instruments and high-speed cameras, we will capture enough data to solve the mystery. Or perhaps ball lightning will remain what it has always been, a fleeting, luminous visitor from the hidden forces of nature. For now, when a thunderstorm rolls in and the sky begins to rumble, some people still glance out their windows. Not just for lightning bolts, but for those rare, glowing spheres that float in silence, reminding us how much of the world remains unexplained. The longevity of tardigrades. In the hidden world of the microscopic, there lives a creature so resilient it seems almost indestructible. It's called a tardigrade, though many affectionately know it as the water bear or moss piglet because of its plump, segmented body and slow, lumbering gait. At less than a millimeter long, tardigrades are easy to overlook, clinging to damp mosses or drifting in droplets of water. But these tiny animals possess powers that defy imagination. They can survive being frozen near absolute zero. They can endure heat hot enough to boil water. They can shrug off doses of radiation that would obliterate most life forms. And astonishingly, they can even survive the vacuum of space. How do these fragile-looking creatures endure such extremes? And what secrets do they hold about the limits of life itself? Tardigrades were first discovered in 1773 by German zoologist Johann August Ephraim Goes, and later named tardigrada, meaning slow stepper, for their deliberate movements. Under a microscope, they look like something out of science fiction, tiny 8-legged bears with claws and a tubular mouth for piercing plant cells. For centuries, they were scientific curiosities. But it wasn't until the 20th century that their true nature as survival champions began to emerge. One of the tardigrade's most astonishing abilities is its power to enter a state called cryptobiosis. In this condition, a tardigrade effectively suspends its life processes, curling into a dried-out ball called a ton. In the ton state, tardigrades lose almost all their body water and lower their metabolism to near zero. In this death-like stasis, they can persist for decades, perhaps even centuries, waiting for water to return. Once rehydrated, they reawaken and resume life as if nothing happened. This incredible adaptation allows them to endure drought, freezing, and other deadly conditions. The extremes tardigrades can tolerate are mind-boggling. They have survived temperatures as low as -328 degrees Fahrenheit, and as high as 304 degrees Fahrenheit. They have endured crushing pressures 6 times greater than those found in the deepest ocean trenches. They can withstand radiation levels hundreds of times higher than what would kill a human. And in 2007, tardigrades became the first animals to survive exposure to the vacuum and radiation of outer space. When researchers sent them aboard a European Space Agency satellite, the tiny creatures spent 10 days outside Earth's atmosphere, bombarded by cosmic rays and ultraviolet radiation. Many of them revived and reproduced after returning to Earth. How do tardigrades achieve such feats? Scientists are only beginning to unravel their secrets. One key lies in their unique proteins. Tardigrades produce a molecule called trehalose, which helps protect their cells by replacing water and stabilizing membranes during drying. More recently, researchers discovered a special protein unique to tardigrades called SUP. This protein wraps around DNA, shielding it from damage by radiation and oxidative stress. In lab experiments, inserting the JUSUP gene into human cells reduced DNA damage from X-rays by up to 40%. A tantalizing hint that tardigrade biology might someday inform human medicine. Tardigrades also produce a type of bioglass that encases and protects their cells when desiccated, much like amber preserving ancient insects. Combined with antioxidant enzymes and robust repair mechanisms, these adaptations create a biological armor against the harshest environments. But the tardigrade's resilience raises even deeper questions. Are they simply extreme survivors, or could their biology hint at possibilities for life beyond Earth? Some scientists speculate that tardigrades, or creatures like them, might survive on icy moons such as Europa, or in the thin atmosphere of Mars. Others wonder whether tardigrade-like cryptobiosis could inspire technologies for preserving human organs, or even entire humans for long-duration space travel. The longevity of tardigrades also forces us to rethink what it means to be alive. When a tardigrade enters its ton state, is it truly living, or is it in a state between life and death? How long can a creature persist in such suspended animation before it crosses a threshold from which it cannot return? Experiments have revived tardigrades after 30 years in a ton state, but could some survive for centuries or even millennia, waiting patiently in the dust until water returns? Despite their astonishing toughness, tardigrades are not invincible. They are vulnerable when active and hydrated, just like other animals. And certain conditions, such as extreme heat while hydrated, can still kill them. Yet their extraordinary strategies for survival make them icons of endurance in a fragile world. As we peer closer at these tiny creatures, we find more than just a scientific curiosity. Tardigrades remind us that life can take forms far stranger and more resilient than we ever imagined. They show us that survival is not always about strength or size, but about adaptability and patience. In their microscopic bodies lies the power to endure the unendurable, and perhaps a glimpse of life's potential to persist across space and time. The Mpemba effect. Imagine placing 2 containers of water into a freezer, one filled with hot water, the other with cold. Common sense and basic science suggest the cold water should freeze first. After all, it's already closer to freezing. But sometimes, against all logic, the hot water freezes more quickly. This strange phenomenon is called the Mpemba effect, and it has puzzled observers for centuries. Why would heat, the very opposite of freezing, help water solidify faster? Scientists have offered theories, experiments, and debates, but to this day, no single explanation fully resolves the mystery. The effect takes its name from Ernesto Mpemba, a Tanzanian student who stumbled upon it in the 1960s. While making ice cream in a school experiment, Mpemba noticed that his mixture froze more quickly when it started out hot than when it was allowed to cool first. Intrigued, he asked his teachers about this, only to be dismissed. But Mpemba's persistence led him to bring the question to physicist Dennis Osborne, who helped him test and published the findings. Their paper, titled Cool, described an effect that had also been reported throughout history. Indeed, the Mpemba effect is not a modern discovery. Aristotle wrote of warm water freezing more quickly than cold, as far back as the 4th century BCE. Later thinkers like Roger Bacon and René Descartes also mentioned the phenomenon. Yet despite its ancient roots, the effect remains poorly understood. Modern experiments confirm that under certain conditions, hot water can freeze faster than cold, but the circumstances are delicate and difficult to reproduce consistently. Why would this happen? At first glance, it seems impossible. Before hot water can freeze, it must cool down to the same temperature as the cold water, so how could it ever overtake it? The answer lies in the complexity of water itself, one of the most unusual and paradoxical substances in nature. Water doesn't behave like a simple liquid. It expands when it freezes, its molecules form intricate hydrogen bonds, and its properties depend heavily on temperature and pressure. These quirks might hold the key to the Mpemba effect. Scientists have proposed several possible explanations, each capturing part of the truth but leaving unanswered questions. One possibility involves evaporation. Hot water evaporates more quickly than cold water, reducing its mass. With less water to freeze, the process might finish sooner. This seems plausible, but experiments show the Mpemba effect can occur even when evaporation is minimized, suggesting other factors are at play. Another theory points to convection currents. Hot water cools unevenly, with warmer portions rising and cooler portions sinking. This creates strong circulation within the container, distributing heat more effectively and allowing it to shed energy faster. Cold water, by contrast, may cool more sluggishly, with less internal motion. Dissolved gases might also play a role. Heating water drives out dissolved oxygen and carbon dioxide. Degassed water behaves differently as it cools, potentially altering the freezing process. Some studies suggest that changes in the structure of water as it loses gases could influence how ice crystals form. Supercooling offers yet another explanation. When water cools below its freezing point without forming ice, it enters a delicate, unstable state. A slight disturbance can trigger rapid freezing. Perhaps hot water, by losing impurities or gas bubbles during heating, is less likely to supercool and therefore begins to freeze sooner. More exotic ideas involve changes in hydrogen bonding. Some researchers suggest that heating water breaks down clusters of hydrogen bonds, allowing molecules to rearrange themselves in ways that facilitate faster ice formation later. Yet none of these theories fully explain the effect in every case. Experiments produce conflicting results, depending on the container shape, water purity, surrounding airflow, and measurement methods. Sometimes the Mpemba effect appears. Sometimes it doesn't. This inconsistency has led some scientists to argue that the effect is not a single phenomenon, but a family of overlapping processes. The Mpemba effect is fascinating, not just because it challenges intuition, but because it reminds us how much we still don't know about something as ordinary and essential as water. Despite centuries of study, water remains one of the strangest substances in the universe. Its molecules dance to rules that defy our simple models, and its behavior in extreme conditions continues to surprise us. Beyond curiosity, understanding the Mpemba effect could have practical implications. Insights into freezing dynamics could improve refrigeration, cryopreservation, and even climate science, where the formation of ice plays a critical role in global systems. But perhaps the greatest lesson of the Mpemba effect is philosophical. It shows us that the world doesn't always behave as we expect. It invites us to question our assumptions, to look closer at familiar things, and to embrace the wonder of discovery. So the next time you see water boiling or ice forming, remember that even in these everyday transformations, mysteries still lurk, mysteries that have confounded minds from Aristotle to Mpemba, and that continue to whisper of secrets yet to be revealed. The WOW signal. On a warm August night in 1977, a massive radio telescope at Ohio State University swept its electronic ear across the heavens. The Big Ear Radio Observatory, as it was called, had been scanning the skies for years as part of SETI, the search for extraterrestrial intelligence, listening for faint whispers that might reveal we are not alone. Mostly it heard the static hum of space and occasional signals from earthly satellites. But on August 15th, something extraordinary happened. For exactly 72 seconds, the telescope picked up a powerful, narrow-band radio signal coming from the direction of the constellation Sagittarius. It was so strong and so unusual that when astronomer Jerry Emmons circled the data printout, he scribbled one word in the margin: "Wow." That handwritten note gave the signal its name, the WOW signal. And nearly 5 decades later, it remains one of the most tantalizing mysteries in the search for life beyond Earth. Was this a message from an alien civilization, or just a strange cosmic coincidence? The WOW signal stood out for several reasons. First, it came at a very specific frequency, 1420 megahertz, corresponding to the hydrogen line, the natural radio emission of neutral hydrogen atoms. Hydrogen is the most abundant element in the universe, and some SETI researchers had long suggested that an intelligent species might use this frequency as a kind of universal hailing channel. The signal was also exceptionally strong, 30 times stronger than the background noise, and highly focused, suggesting it wasn't a natural broadband source like a pulsar or quasar. Yet despite its intensity, the WOW signal lasted only 72 seconds, the time it took for the Big Ear's beam to sweep over that part of the sky. Then it vanished. The telescope scanned the same region several times afterward, but the signal was never detected again. This fleeting nature is part of what makes the WOW signal so puzzling. If it came from an intelligent source, why did it not repeat? Over the years, scientists have searched for mundane explanations. Could it have been a reflection from a satellite? An aircraft? A secret military transmission? None of these possibilities fit perfectly. The Big Ear as design meant that terrestrial signals would usually appear in both of its two beams, but the WOW signal appeared in only one. That suggests the signal originated far beyond Earth. Some researchers have suggested that the signal could have come from a comet passing through the telescope's field of view. Comets can emit hydrogen radio waves as their icy shells vaporize. In 2017, a team proposed that Comet 266P Christensen, which was in the right part of the sky at the time, might be the culprit. However, this explanation has its critics. Comets tend to emit weak, diffuse radio noise, not the focused, powerful burst observed in the WOW signal. The possibility that the WOW signal was artificial, a deliberate transmission from an alien civilization, remains the most exciting and controversial idea. If true, it would be the first sign that we are not alone in the cosmos. Some CT researchers speculate that the signal could have been a beacon, an intentional message broadcast to alert others to the sender's existence. Others suggest it might have been an accidental leakage, like the way Earth's early radio and TV signals have leaked into space for nearly a century. But skeptics point out that extraordinary claims require extraordinary evidence. A single, unrepeatable signal is not enough to prove the existence of extraterrestrial intelligence. It could be a fluke, a rare and poorly understood cosmic phenomenon that just happened to mimic an artificial source. Efforts to redetect the WOW signal have continued for decades. Radio telescopes around the world, from Arecibo to the Allen Telescope Array, have scanned the region of Sagittarius again and again. So far, they have found nothing. It's as if someone spoke a single word across the vastness of space and then fell silent forever. The WOW signal haunts us because it represents both the promise and the frustration of the search for extraterrestrial life. It was strong enough to raise our hopes, yet fleeting enough to elude confirmation. It reminds us how vast the universe is, and how difficult it might be to find others within it. Perhaps there are countless civilizations out there, but their signals are rare, faint, or transient. So much so that catching one is like trying to hear a whisper in a hurricane. Or perhaps the wow signal was never a message at all. Perhaps it was a quirk of nature, a glitch in the instrument, or an unknown astrophysical event that just happened to pass our way once and never again. Until we detect a similar signal and study it in detail, we may never know. Still, the wow signal endures as a symbol of curiosity and possibility. It reminds us that even in a universe filled with noise, there are moments of mystery that make us pause and wonder. Are we truly alone? Or is someone, somewhere, waiting for us to listen again? Antimatter asymmetry. The universe as we know, it is built on matter. Stars, planets, clouds of gas, oceans, trees, and even your own body are all made from tiny particles, protons, neutrons, and electrons. But according to our best scientific theories, when the universe began in the Big Bang nearly 14 billion years ago, it should have created matter's mirror image in equal measure. Antimatter. For every proton, there should have been an antiproton. For every electron, a positron. When matter and antimatter meet, they annihilate each other in a flash of pure energy. So, if there was once an equal balance, why didn't everything cancel out in the first instant, leaving behind nothing but light? Why does any matter remain at all? Why is there a universe instead of an empty void? This is the mystery of antimatter asymmetry, and it is one of the greatest unsolved problems in physics. Somewhere in the early universe, a tiny imbalance must have occurred, a preference for matter over antimatter, just enough to leave behind the particles that eventually formed galaxies, stars, and us. But what caused this imbalance? Why does nature favor matter? Antimatter was first predicted in 1928 by physicist Paul Dirac, who combined quantum mechanics and special relativity in an elegant equation. His theory implied that every particle has an opposite twin, identical in mass, but with opposite charge. A few years later, antimatter was discovered experimentally, confirming Dirac's prediction. Antimatter isn't just a mathematical curiosity. It's real and behaves exactly like matter until the two meet. When they do, they annihilate in an explosion of energy. In the lab, physicists can create antimatter in particle accelerators. We know it exists and follows the same physical laws as matter. So the big question is, what happened to all the antimatter that should have been created in the Big Bang? At first glance, it seems that matter and antimatter are perfect opposites, destined to cancel out in equal quantities. But in the 1960s, experiments began to uncover tiny cracks in this symmetry. In 1964, physicists James Cronin and Val Fitch observed a phenomenon called CP violation in the decay of certain particles known as kaons. CP violation means that the laws of physics aren't perfectly symmetrical when particles are swapped for their antiparticles, and their spatial coordinates are flipped. This hinted at a mechanism by which matter and antimatter could behave slightly differently. However, the amount of CP violation observed so far is far too small to account for the overwhelming dominance of matter in the universe. It's as if nature's bias for matter was only revealed in subtle whispers, not loud enough to explain why all the antimatter vanished. Physicists are now searching for additional sources of asymmetry. Theorists suspect that in the searing hot moments after the Big Bang, exotic particles may have existed that no longer appear in today's cooler universe. These particles might have decayed in ways that slightly favored matter over antimatter, leaving a tiny surplus of matter behind. This process, known as baryogenesis, remains hypothetical. Experiments around the world are hunting for clues. At CERN's Large Hadron Collider, scientists create collisions at energies similar to those just after the Big Bang, hoping to see hints of new physics. The Alpha experiment traps antihydrogen atoms to study their properties and see if they behave exactly like hydrogen, or if there are subtle differences. Neutrinos, the ghostly particles that stream through the Earth in their trillions, may also hold answers. Some models suggest that neutrinos could exhibit their own form of CP violation, tipping the cosmic scales. But so far, the mystery persists. No experiment has uncovered a mechanism strong enough to explain the imbalance. The universe remains stubbornly matter-dominated, with only traces of antimatter found in cosmic rays and particle accelerators. This asymmetry is not just a technical problem for physicists. It touches on the deepest question of existence. If matter and antimatter had truly been created in perfect balance, there would be no stars, no planets, no life. The universe would be a uniform sea of photons, empty of structure or meaning. In a sense, we exist because of a tiny imperfection in the early universe, a cosmic quirk that tipped the scales in favor of matter. Without it, there would be no one here to ask why. Some theorists have speculated about even stranger possibilities. Could there be regions of the universe where antimatter dominates, separated from matter by vast empty voids? Could the universe be symmetrical on the largest scales, with matter and antimatter forming cosmic yin and yang? Or could our understanding of space, time, and symmetry be incomplete in ways we can't yet imagine? For now, the puzzle remains. Antimatter asymmetry is one of those rare mysteries that bridges the smallest scales of particle physics with the largest scales of cosmology. It reminds us how fragile and improbable our existence is. Somewhere in the chaos of the early universe, the dice rolled ever so slightly in favor of matter. And because of that, we are here to wonder at the stars, to ask questions, and to seek answers in the quiet laboratories and great particle colliders of our time. Perhaps one day we will discover the mechanism that broke the symmetry, revealing the hidden story of why there is something instead of nothing. Until then, the universe's preference for matter remains a silent enigma, written into the fabric of existence itself. The origin of cosmic magnetism. Magnetism is all around us. It guides a compass needle, protects Earth from solar winds, and shapes the glowing curtains of the aurora borealis. On larger scales, magnetism threads through stars, planets, and even entire galaxies. Yet despite its ubiquity, magnetism hides an unsolved cosmic mystery. Where did it come from in the first place? How did the universe, born as a hot neutral plasma after the Big Bang, come to be threaded with invisible magnetic fields that stretch across vast regions of space? This question, the origin of cosmic magnetism, remains one of the great puzzles of astrophysics. We know that many celestial bodies are magnetic. Earth has a magnetic field generated deep within its molten iron core, acting like a giant bar magnet in space. The Sun has a magnetic field that twists and snaps, giving rise to sunspots, flares, and coronal mass ejections. Even gas giant planets like Jupiter and Saturn have powerful magnetic fields. On larger scales, entire galaxies are laced with magnetic fields that influence how gas moves and stars form. And beyond galaxies, astronomers have detected faint magnetic fields stretching across the cosmic web, the vast filaments of gas and dark matter that connect galaxy clusters. These fields play crucial roles in shaping cosmic evolution. They guide charged particles, regulate star formation, and help protect planetary atmospheres from being stripped away by stellar winds. But while we understand how planets and stars maintain their magnetic fields, through processes like the dynamo effect, we don't yet understand how the first seeds of magnetism appeared in a universe that, at its birth, should have been magnetically sterile. One key concept is the dynamo effect, which explains how celestial bodies sustain magnetic fields. In Earth's core, for instance, moving liquid iron conducts electricity, which in turn generates magnetic fields. These fields can reinforce and sustain themselves as long as the fluid motion continues. The sun's magnetic field is generated in a similar way by turbulent motions of plasma in its interior. But dynamos require a seed field to amplify. If the universe started with no magnetism at all, what provided the first seed fields? Astrophysicists have proposed several possibilities. One idea is that tiny magnetic fields were generated during the early universe, perhaps in the chaotic moments of the Big Bang. Quantum fluctuations or phase transitions in the primordial plasma could have given rise to weak, tangled magnetic fields. These primordial seed fields would have been unimaginably faint, but over billions of years, they could have been amplified by cosmic dynamos in stars and galaxies. Another possibility is that seed fields formed later, as the first stars and galaxies ignited. When ionized gas flows through shock waves, such as those created by supernova explosions or galaxy collisions, it can generate weak magnetic fields through a process called the Biermann battery. In this mechanism, slight differences in electron and ion motion create small currents, which produce magnetic fields. Over cosmic time, these tiny fields could have been stretched, twisted, and amplified into the larger-scale magnetism we observe today. Recent observations hint that magnetic fields may be more ancient and widespread than we thought. Astronomers using radio telescopes have detected magnetic fields in vast, empty regions between galaxy clusters, suggesting that magnetism pervades even the most desolate parts of the cosmos. This finding raises intriguing questions. Are these fields relics from the primordial universe? Or did they form later and spread outward from galaxies? The origin of cosmic magnetism is not just a theoretical puzzle, it's also a practical challenge. Simulating magnetism on cosmic scales is incredibly complex, requiring models that capture both small-scale plasma physics and the vast, dynamic evolution of galaxies and clusters. As computing power grows, scientists are creating ever more detailed simulations of cosmic magnetism, testing different ideas about how seed fields might have arisen and evolved. Solving this mystery could have far-reaching implications. Magnetic fields influence how galaxies grow, how cosmic rays travel through space, and even how stars and planets form. Understanding their origins might also shed light on deeper questions about the universe's infancy, such as what happened during cosmic inflation, or how the first structures in the cosmos took shape. Some researchers have proposed even more exotic origins for cosmic magnetism. Could unknown particles or forces in the early universe have played a role? Could magnetic fields be linked to dark matter or other hidden components of the cosmos? Or is magnetism simply an inevitable feature of any universe filled with moving ionized gas? For now, the origin of cosmic magnetism remains an open question, a reminder that even in a universe governed by well-understood physical laws, there are still hidden forces shaping the grand design. Invisible and silent, magnetic fields thread the cosmos like a hidden scaffolding, guiding the dance of particles and energy across billions of light years. We live in a universe where magnetism protects our world, shapes our star, and guides charged particles across interstellar space. And yet, we still don't know how it all began. Perhaps, as we peer deeper into the void with next-generation telescopes, we'll catch a glimpse of magnetism's ancient roots, a faint echo of the moment when the universe first sparked with invisible lines of force. Why we sleep. Each night, as darkness falls, we lie down, close our eyes, and surrender to sleep. Hours slip by in unconsciousness while our bodies lie still, and our minds drift through surreal landscapes of dreams. When we awaken, we feel refreshed, but also strangely vulnerable, aware that for a third of our lives, we are suspended in a state we cannot fully control or explain. Sleep feels natural, even inevitable. Yet, despite decades of research, science still doesn't fully understand why we sleep or what dreams truly are. At first glance, sleep seems paradoxical. In a world where survival depends on alertness and quick reactions, why would any creature evolve to spend hours in a defenseless, unresponsive state. To biologists, this question is profound. Sleep is so universal in the animal kingdom that it must serve an essential purpose. Birds sleep, whales sleep, even insects and worms display sleep-like states. And when deprived of it, organisms suffer and sometimes die. Clearly, sleep is not wasted time. But what is it for? One theory holds that sleep is primarily restorative. During waking hours, the brain consumes vast amounts of energy and builds up metabolic waste. As we sleep, the body repairs damaged tissues, replenishes energy stores, and strengthens the immune system. In the brain, a remarkable cleaning process unfolds. Studies show that cerebrospinal fluid flows more freely during sleep, washing away toxins such as beta amyloid, which is associated with Alzheimer's disease. In this way, sleep may act like a nightly housekeeping service for the nervous system, clearing out the debris of wakefulness. But sleep is not just for the body, it is deeply tied to memory and learning. During the day, we take in information, form impressions, and encounter new experiences. At night, the brain consolidates these memories, strengthening important connections and pruning away irrelevant ones. This process likely occurs during different stages of sleep. In slow-wave sleep, deep and dreamless, the brain seems to focus on stabilizing facts and skills. In rapid eye movement sleep, when vivid dreaming occurs, the brain may integrate emotional experiences and explore creative associations. Dreams themselves are a mystery within a mystery. For centuries, philosophers and poets have speculated about their meaning. Are dreams messages from the subconscious, as Freud believed? Random firings of neurons, as some neuroscientists suggest? Or are they a playground for the brain to simulate challenges and rehearse solutions? Modern research indicates that dreams may help us process emotions, test social scenarios, and even problem solve. Studies have found that people who dream about a task often perform better at it the next day. Perhaps dreams are not just passive experiences, but active mental workouts. Yet sleep remains only partially explained. If its purpose is restoration and memory consolidation, why do some animals, like dolphins, sleep with only half their brain at a time? Why do newborn babies spend more time in REM sleep than adults? And why do we need such a complex cycle of different sleep stages, rather than a single uniform state of rest? Depriving a person of sleep leads to rapid and alarming consequences. Within a day or two, attention falters, emotions become erratic, and memory suffers. Prolonged sleep deprivation causes hallucinations, immune dysfunction, and even death in extreme cases. Clearly, sleep is as essential as food or water. But why has evolution chosen sleep, rather than some alternative method of restoration that wouldn't require complete unconsciousness? Some researchers propose that sleep evolved to conserve energy during periods of inactivity. Others argue it serves as a way to keep animals safely out of harm's way during dangerous hours. But these ideas don't fully account for the intricate neurological processes that unfold while we sleep. The deeper truth may be that consciousness itself is metabolically expensive, and turning it off periodically is the price of having such a powerful brain. In the modern world, sleep is often undervalued. Artificial light, screens, and relentless schedules push sleep to the margins. Yet the more we study it, the clearer it becomes that sleep is not optional. It is a fundamental pillar of health, creativity, and even sanity. Losing sleep means losing the intricate symphony of cellular repair, memory integration, and emotional recalibration that occurs each night. Perhaps the mystery of sleep is not just scientific, but existential. When we sleep, we surrender our waking selves and enter a different kind of being. Time loses its flow. The boundaries between reality and imagination dissolve. We dream, we heal, we reset. And when we wake again, the world feels new, as if we too have been renewed. Until science can fully explain why sleep is so essential, we are left with an ancient truth. Sleep is a journey we must take, night after night, as vital and mysterious as life itself. Why the universe exists. Why is there something rather than nothing? It's one of the oldest and deepest questions humanity has ever asked. Philosophers, theologians, and scientists alike have struggled with it, often arriving at wildly different conclusions. At its core, the question asks why anything exists at all. Space, time, matter, energy, even the laws of physics themselves. It's a question that cuts through layers of scientific knowledge and philosophical speculation, straight into the heart of the unknown. And to this day, science cannot provide a definitive answer. The universe exists, but why? The mystery begins with the recognition that the universe didn't have to exist. There is nothing logically necessary about a universe with galaxies, stars, and planets. It could have been empty. It could have been lifeless. Or it could have never existed at all. Yet, here we are, thinking, breathing, wondering, surrounded by a cosmos bursting with light, structure, and complexity. When we look around and ask how it all came to be, we find explanations for individual parts, how stars form, how galaxies evolve, how matter behaves. But those explanations all rest on deeper assumptions. Assumptions about the very existence of space, time, and the physical laws that govern them. One of the dominant scientific explanations for how the universe came into being is the Big Bang theory. According to this model, the universe began around 13.8 billion years ago as a singularity, a point of infinite density and temperature. In the first moments, space and time themselves began to expand rapidly, giving rise to the cosmos we observe today. This expansion cooled the universe, allowing matter to form and eventually coalesce into stars and galaxies. The evidence for the Big Bang is strong. The cosmic microwave background radiation, the abundance of light elements, and the redshift of distant galaxies all point to a universe that had a beginning. But the Big Bang theory describes how the universe evolved, not why it exists in the first place. Some theories attempt to go beyond the Big Bang. For example, quantum cosmology suggests that the universe could have arisen from a quantum fluctuation in a vacuum. According to this idea, the vacuum is not truly empty, but a seething foam of virtual particles and energy fields. In certain conditions, such a fluctuation could give rise to a universe, a bubble of space-time that expands and evolves according to physical laws. This process might not require anything external to the universe, and in that sense, it offers a kind of something from nothing. But then we are left asking, where did the vacuum come from? Why do the laws of quantum mechanics exist? Why is there anything capable of generating fluctuations at all? Others propose that the universe is part of a larger multiverse, a vast collection of universes, each with its own laws and constants. In this view, our universe may be just one bubble in an endless cosmic foam. Some bubbles collapse, others expand, and a few, like ours, develop the conditions for life. This idea could explain why the physical constants in our universe appear finely tuned. If there are countless universes, it's not surprising that at least one would support observers who wonder why the universe exists. But the multiverse theory, while fascinating, pushes the question back rather than answering it. Why does the multiverse exist? Why are there any laws at all that permit universes to pop into being? Philosophers have long grappled with this mystery. Some argue that nothingness is unstable or logically impossible, that something must exist because pure non-existence is inherently flawed or contradictory. Others suggest the universe exists for no reason at all. That existence is simply a brute fact, a reality that needs no further explanation. This idea can be unsatisfying, but it highlights the possibility that not all truths have deeper causes. There's also the theological perspective, which posits that a divine being created the universe. In this view, God is the necessary being, the ultimate cause that explains why anything exists at all. But even here, skeptics ask, why does God exist? Why not nothing, not even God? Any explanation, it seems, eventually hits a wall. Perhaps the very structure of logic and causality breaks down when we try to apply it to the origin of existence. Maybe why questions only make sense within a universe, within time and space. Asking why the universe exists could be like asking what's north of the North Pole, a category mistake. From this perspective, existence might not need a cause in the way we typically understand it. It might be the background condition for everything else, not something that itself requires explanation. Some physicists and philosophers have even proposed that the universe created itself. According to one interpretation of quantum gravity, time itself could be an emergent phenomenon, something that arises only after the universe comes into being. If that's the case, then the idea of a before the universe might not be meaningful. The universe may have no origin in time, because time began with the universe. In this view, asking why the universe exists is like asking why a circle has no corners. The question doesn't fit the shape of reality. Still, the question refuses to go away. Even if time began at the Big Bang, even if the laws of physics allow for spontaneous creation, even if the multiverse exists, we are still left with that deep, unsettling mystery. Why is there anything at all? Why are there laws instead of chaos? Why is there light instead of darkness? Some thinkers suggest we will never know the answer, not because it's unknowable, but because we are not equipped to ask the question in the right way. Just as a dog cannot understand calculus, perhaps human minds are not evolved to comprehend the roots of existence. Our intuition, shaped by survival in a physical world, may be too limited for the scale of the question. Yet we keep asking, driven by a sense of wonder that has fueled science, philosophy, and religion for thousands of years. Others hold on to hope. Perhaps one day we will discover a final theory, a framework so elegant and complete that it not only explains how the universe behaves, but also why it exists. Perhaps existence will turn out to be necessary after all, a natural consequence of mathematical structure or logical inevitability. In such a theory, the universe would not be an accident, but the only possible outcome. Until then, we live in a cosmos filled with stars, galaxies, and the miracle of consciousness. We are part of the mystery we seek to solve. The universe does not owe us an answer, yet it invites us to keep asking the question. In the silence between galaxies, in the gaps between what we know and what we long to understand, the question persists. Why is there something instead of nothing?